Morning, everybody. We'll go ahead and get started here. So we have two sections that are a little bit shorter today. And so we're going to do 5.2 and we'll also be able to do 2.6 as well. These will be the last two sections of new material for the test. So yes, these two sections we're doing today are going to appear on the test that we have coming up this Wednesday. Now, tomorrow is going to be a review. I'm going to go over one of the versions of the sample test. If you look at the sample test, there's a version A and a version B. I do one version in class, and I leave the other one for you to do on your own for practice. So we're just going to do that tomorrow for lecture. We'll just go through that. And then if you have any other questions, you can ask those as well. So let's go ahead and get started here with 5.2. So first of all, here we're talking about a one-to-one function because it's part of a definition for what we need for inverse functions, which we'll get to in a little bit. So here's the definition for a one-to-one function. It's one-to-one, and we're assuming again that A and B are in the domain, and these 2 points that we have are not equal to each other. So what this is saying is that for every y value, there can only be one x value. That's what all this really translates into. It basically says that if the y values equal each other, then the x values must equal each other. And so that's basically what it says here. So then we have something that's called a horizontal line test to determine whether something is one-to-one or not. And basically you draw a horizontal line through like that. And if it hits the graph more than once, then it's not one-to-one. Now, of course, in order for it to be one-to-one, it has to be considered a function first. So for these problems, you actually want to do a quick check to make sure it passes the vertical line test. And if it does, we know it's a function, and then we can proceed and do the horizontal line test. So for this one here, it would definitely pass the vertical line test. If you draw a vertical line through any of these, it would definitely pass and it would be considered to be a function. However, it does not pass the horizontal line test because for this single y value, we have multiple x values. And so this right here, we're going to say is not one-to-one. Okay, so it's not one-to-one. All right, so it has to hit it only one. The horizontal line has to hit the graph only once for it to be considered one-to-one. The next one, if we pass a horizontal line here or here, these pink lines here, anywhere you draw a horizontal line, it'll only hit the graph once. And so the second one is going to be one-to-one. Now you got to be careful with part C, because part C, notice if you draw a vertical line that we have here, it's hitting the graph more than once. So therefore, it says that because it doesn't pass the vertical line test, that means it's not a function, and therefore it cannot be not one-to-one either. Now you might be thinking, well, wouldn't that pass the horizontal line test? Yeah, every horizontal line would only hit the graph once, but remember, in order for it to be one-to-one, it has to be a function first. Okay, so if it doesn't pass the vertical line test, then automatically you don't do the horizontal one. Automatically, it's not one-to-one, because in order for it to be one-to-one, it has to first be a function in the first place. So in that case, it's not considered one-to-one. So again, every y value can only have one x value. That's what we mean by one-to-one. And the reason why we're talking about one-to-one is talking about that's actually a definition of what it means to be an inverse function that we have down here. So in order for you to have what are called inverse functions, they have to be one-to-one, first of all. And then G is the inverse of F if the conditions are true. So the reason why we do 5.1 and 5.2 together is because 5.1, we talked about how to do this composition functions. Well, this ends up being a definition. This lets you know whether something is an inverse function or not. If it's an inverse function, that means it's going to pass this test here. If we do f of g of x and we get x, and we get g of f of x and we get x for that, then that's the test to know whether two functions are inverses. There's also a way to tell if they're inverses graphically, and we'll take a look at that a little bit later. Now, once you know that something is an inverse, the inverse notation that we use is this little -1 that you see up there. So inverse of f is f with a little -1 on it. So that's what we mean by inverse. The inverse of f is this little thing right here. It doesn't mean f raised to -1 power. That's just the symbol we use to indicate an inverse. Now here is a definition that is true. Now when you have something like this, we looked at graphs a little while back, and we said that if you put an x value in, and you look at the graph and you get a y value. So basically what this is saying is that the point x, y is on the original graph of f of x. Well, if you take this point and you move it over to the inverse, what happens is the x and the y actually switch on the inverse. So if you have one point x, y that's on the original one, we know that the point y comma x is actually going to be on the inverse. That's actually what this definition here tells us. And we can use that for this one right here. If you're given f of 10 equals 14, find the inverse of 14. Now, you don't have to actually know what that function is if you just use this definition right here. Okay, so this definition is saying if this is x and this is y, then if you have a y here, that means the x value must appear here. So if I have f of 10 equals 14, that means this is the x and this is the y. If I find the inverse, that means this is the y. So this is going to be equal to the x value. So f inverse of 14 is going to be equal to 10. Okay, and again, this comes directly from this definition that we have here. Okay, so that's how we can find the x value right away without actually knowing what the inverse function is. We don't have to plug any numbers in here. We're just using this particular identity, this property right here. Okay, so next we're going to take a look at the graphs and see what happens when we have inverses. So it says, given this and this, verify if they're inverses. Now we're going to verify this algebraically first, and then we're going to graph them and take a look at that. Now the two tests that we have to do to determine whether they're inverses or not is to do this test. We want to find f of g, and we want to find g of f of x. If we get x's for both of these, then that's going to automatically tell us that that's going to verify their inverses. That's how you do the verification step. You just find f of g and g of f here. So first of all, f of g of x, we have to, first of all, remember the definition from the previous section, f of g of x there, and we have g of f of x right here. Okay, so we've got both of those, and we have the definitions. Next, what we're going to do is we're going to remove the g of x inside, replace it with the formula that goes with it. So we're going to do f of 1/2 x plus 1/2. Okay, that means that you're going to put all this into the f function wherever there's an x. So originally, I have 2 times a blank minus 1. Originally, I had this x here. I'm going to remove it. Replace it with what part is inside the parentheses, 1/2 x plus 1/2. Then you're going to multiply by 2. 2 times 1/2 is just 1, so that's x. 2 times 1/2 is just plus 1 there, and I have a minus 1. And I get x. Okay, so I've shown that doing the first part, I get an x. In order to verify, I have to do the other way as well. I have to do g of f of x and show that equals x as well. So this definition says that I'm going to remove, start with the inside. The inside, I'm going to take out f of x, replace it with 2x minus 1. And then I have to put the 2x minus 1 into the g function. What that'll look like is I have a 1/2. I'm going to take out the x. Okay, so x goes away, I replace it with 2x minus 1, and then 2x minus 1 goes in there. And I'm going to multiply each of these by the 1/2. So I get 1/2 times 2 is just x. 1/2 times minus 1 is a minus 1/2, and I get plus 1/2. These are going to cancel out. Once again, I get x. Okay, so now I've shown that doing both of these compositions allowed us to get x. That verifies algebraically that these are inverses. So the next thing we want to do is to graph both of these. That's what it tells us to do. Okay, so let's graph 2x minus 1. How we graph that is we go to the y-intercept first. Y-intercept is, it'll cross at -1. Now the slope here is 2, and that's really like 2 over 1. So from this point, I'm going to go up 2 units and over 1 unit. Up 2 over 1. I can just keep doing that, up 2 over 1, up 2 over 1. I can just do that however many times I want. I can do that to get these just like that. And so this right here is going to be the f of x. Next thing on the graph is the 1/2 x plus 1/2. So 1/2 is the y-intercept. And then the 1/2, I'm going to go up 1 and to the right, up 1 and to the right. I can just keep doing that over and over again. So I got, so up 1, actually that spot isn't, that's in the wrong spot. If I go up 1, it's at a 1/2 right here. So it should be right there. If I go up 1 over a 1/2, it'll be right here. So that's where I have it. And it looks like it'll cross over my other line right there at the point 1, 1. So they kind of both intersect there at 1, 1. This is g of x. Now, because I get x as a result here, I want to go ahead and graph that one as well. I'm going to do that with a dotted line. So if I want to graph the line y equal x, that's just a line that goes through 0, 0, and it has a slope of 1. And so it's just basically going to be a 45-degree line like that. It kind of goes through up 1 over 1, up 1 over 1, up 1 over 1, and so forth. I can do to get that graph. So this dotted line is the line y equals x. Now, one thing that you're going to notice about this is that if you imagine this dotted line as a fold line, we can fold these two graphs over, and they're going to lay on top of themselves right here. So the line y equal x ends up being a fold line or a line of symmetry. So that's why when you compose and put these together, we end up just getting the fold line as a result here. We get x for both of those. Okay, so that's the significance of why you get an x as a result there. Basically, when you compose these, you just end up getting the fold line that they're both composed to. Okay, so you have both of these here and both of those there. So anytime you see a line that's it's symmetric to the line y equal x, that means those two lines are going to be inverses of each other. Okay, so that's what that means. Graphically, that's how you know they're inverses as well. So there is a question that is in the homework that talks about like visually. What you would do is you want to verify, see which one. It's like a multiple choice thing, and it asks you whether whether they're inverses or not. And so that's basically how you can tell. And so you just look at, they're going to give you some kind of line segment, and it's going to ask you to pick the one that's symmetric. So you just pick the one that looks the mirror image of the line y equal x. That's how you would do one like that in the homework. So there's one like that in there that you'll look at. So again, as I mentioned this earlier, but the notation to write the inverse of f is this one right here. So it's just kind of formally writing that f -1 of x. So again, this does not mean that you're raising f to a -1 power. That just means that that's the notation that you'll have of the inverse. So that's what the little -1 means. Whenever you see that, it means inverse does not mean -1 power. Okay, so the next one, we have another one. We're not going to graph this one here. We're just going to verify that the two are inverses. And so this next one that we're going to do is just going to be algebra only. And again, the way you show something's inverses is you have to show f of g of x, and you're going to show g of, you're going to do g of f of x. Okay, so we'll do that next. Okay, so we've got this. Okay, so whenever you want to verify that something is inverses like this, you just want to show these two steps right here. This first one, f of g of x, is the same thing. We have g with an f of x inside. And this is a g, then we have f of x inside, just like that. Oops, I did the wrong one here. Let's switch that. This one, first one was f of g of x, sorry about that. And this is g of g with an f of x inside. Okay, so that's the two definitions that you want to know. We start with the inside. Okay, so the inside is the, and actually here, I apologize, I'm not using the right notation for you guys. I'm supposed to use the correct notation, so sorry about that. I'm using f and g, but let's go ahead and use what was actually given. So f, so really what we're doing here is we're doing f, I'm just going to write it out this way. Okay, so if we have this, and then we want to do the inverse with the original one put inside. Now we're using the correct notation. Let's just go ahead and write it directly as each of these. So you're putting the inverse into the f, and you're putting the f into the inverse. And so now we're using the correct notation for what the problem gave us. So we're still going to start with the inside. We're going to start with the inverse, which is x squared plus 3. Okay, this has to be put into the original function. Well, the original function is the square root of x minus 3. So we have here, if we put that in there, we have a square root, we have a blank, a minus 3. We're going to get rid of the x and replace it with x squared plus 3. So you can tell here that we're putting in where the x was would be the blank with those parentheses, replacing that with x squared plus 3. We put that inside. From here, we're just going to simplify it. The 3's, those are going to just cancel out, and you end up with the square root of x squared, which is equal to x. Now, there's no plus or minus on here because this is just the positive square root only on this. So there's always a question that comes up of why don't we do plus or minus? It's because you're not actually taking the square root of both sides. It's already given as a square root. So because it's already given as the positive square root, we're not doing plus or minus here in this case. We're just computing all this through and getting the x as a result on that. So we have, that's the answer we get for that one. On the other one over here, we have the inverse, and we're putting the square root inside of it. So we have the inverse with the square root of x minus 3. And we're going to put that into the original one, square root x minus 3 squared plus 3. So again, where the x was, we remove it, replace it with the square root, goes inside there instead. The square and the square root are going to cancel themselves out. We get x minus 3 plus 3, and then that's equal to x as well. So now we verified that both of these, we get x when we do these compositions. So these are verified. We verified those are inverses. Okay, so then nothing else we have to do on that one. Now, next thing that we're going to transition into is, okay, they give us the original one and they give us an inverse. So how do we find that on our own? How can we algebraically find the inverse? That's what we're going to take a look at here next. So it says how to find an inverse algebraically, and there's 4 steps that's here. And we'll walk you through these. We'll do some problems and we'll do this algebraically. So step 1, it says replace the f of x with a y. here's the most important step when you're doing inverses: switch the x and the y. Okay, so you want to switch x and y. Now, the reason why we're doing this is because earlier we talked about when we did that one problem where you have f of x equals y and then the inverse of y equals x. Basically, that's just saying that the point is actually switching on that. So you're switching the x and the y, you're solving for the y, and then you replace the y with the inverse. And I'll walk you through a problem showing all these step by step, and I'll label them 1, 2, 3, 4, so you can see what steps we're going to do. Before we jump into this part about switching the x and the y, I want to go back to the graph that we did here earlier, and I want to show you a couple things from that. So first of all, we have here, if we take a look at this, we actually see, if you look at this point right here, we found this point was 2, 3. So 2, 3. And then if you notice, the graph actually goes through this point right here, which would be 3, 2. So notice that if I have a point on the original one, on the inverse, which we're calling G, notice that the points are actually switched. So we have a 2, 3 and a 3, 2, and that actually happens all along here. We have the same situation that happens on that. So all the points that are on here, they're kind of mirror images. So whatever point you see here, the opposite will be true over there as well. So that's what we end up seeing happen on this. We have also 3, 4, and that means we have so 3, 4 and 4, 3 would be another one that would be switched. So 3, 4 and then 4, 3, 4, 3 would be on there as well. So these are the 2 points I wanted to label so you can see them on the graph: 2, 3 and 3, 2. But that's what we mean by switching the x and y. The inverses are switched. That's why algebraically we do that as well. So replace the f of x with the y. We switch x and y. Once it's switched, then we have to solve for y, and then we just replace the y with the inverse notation, and that's the 4 steps. So now let's go ahead and do a couple of examples where we walk through these 4 steps, and I'll label them for you so you can see how to do each of those. All right, so first thing we want to do, step number 1, and I'll label that. Step 1 is to, we want to replace the f of x with a y. Okay, so originally we're given f of x equals 2x minus 5. So now we're going to do y equals 2x minus 5. That's step number 1. Step number 2 says that we have to switch the x and the y. So everywhere there's a y, we put an x. Everywhere there's an x, we put a y. So we just switch the x and the y there. Now as they're switched, we no longer have this solve for y. So now we have to solve for y in step 3. So I'm going to add 5 to both sides. Okay, so I get x plus 5 equals 2y. Then I need to divide both sides by 2, like that. Then the 2's are going to cancel out. So now my y is equal to x plus 5 over 2. Now step number 4, it just says replace the y with the inverse notation. And I'm also going to switch my equation around so that the inverse comes first. But it's just going to be this right here. It's going to be the inverse of x is x plus 5 over 2. Now it does say they verify, but I'm not going to do that in this problem. You can verify that on your own, and I do that in the written notes. Just want to make sure we have time to cover everything for today. But you would just do the same thing. You would basically just remove the x, replace it with all this here. And then you would also take out the x here, replace it with 2x minus 5. If you do that on both ends, that's going to show you that and verify that those are inverses. But that's the step. So here's the original one was 2x minus 5. And then here's the inverse we found down below here. All right, now this one has a, I went ahead and I crossed out the verification. We're not going to do that part, but I'm going to go ahead and add this because there's a homework problems that have you do something like that where you want to find the domain and range of f of x and the inverse. All right, so we want to do that for both of these. So I want to find, first of all, f of x and the inverse. I want to find the inverse first. So let's go ahead and start that by doing the same 4-step process. Then once we have all those, we'll go ahead and jump into doing this. Okay, so step number 1, we have the f of x. So f of x I'm going to change into a y. So I have y equals square root x plus 7. That's step number 1. Step number 2, switch the x and the y. Okay, so we'll do that. Step number 3, we want to solve for y. Now, in order to do that, we have to square both sides here. So x squared is equal to all of this, y plus 7. 7 squared. So we get x squared is equal to y plus 7. Then we can subtract the 7. Then we get x squared minus 7 equals y. We can just put in the inverse notation for that and flip this around. So the inverse is equal to x squared minus 7. Okay, so that was all that we did, steps 1 through 4. So now we have this one and we have this one here. Okay, so here's something important that I'm going to write down here. The domain of f of x is equal to the range of the inverse. The domain of f of x is equal to the range of the inverse. Likewise, we have the range of the original function, f of x, is equal to the domain of the inverse. Now, the reason why we have this is true is because, remember, we switch x and y. We looked at the graph and we saw that the x and the y are switched when we go from the original function to the inverse. So it makes sense of why the domain and range are also switched, because domain is talking about x's and range is talking about y's. So that is true here. Okay, so this is very important to be able to do these problems in the homework that have to do with domain and range. Let's find the, okay, so domain. So let's write these out. Domain of f of x equals, we're going to do the range of f of x. We're going to do we want to find the domain, and the homework's going to ask for all this. Domain of the inverse. And we want to find the range of the inverse. Okay, so we want to find all this. Domain, range, domain, and range of each one. Well, the domain first, let's do this algebraically for the original one. Now, the original one here, I have a square root, x plus 7. That means that x plus 7 has to be greater than or equal to 0. Remember that whatever you have inside the square root has to be positive only. Okay, you can't take the square root of a negative number. Now, 0 is okay because we're not dividing by 0. We don't have 0 on the bottom of a fraction, nothing like that. So square root of 0 is 0. So we just need to solve this equation. And if we solve that, we end up getting that x is greater than or equal to 7 that we have from the original one. So I just need to put this in interval notation here. That's going to be a bracket with a 7, and that's going to go to infinity. Now, the domain of f of x is equal to the range of the inverse. So now automatically I can put the range of my inverse automatically is now going to be the same thing, the bracket 7 to infinity, because of the definition that we have right here. Now, in order to find the range of f of x, I could look at the graph of it, or I could just find the domain of the inverse. And the domain of the inverse also would affect it. But let's go ahead. I think that'll be easier if we take a look at the graph. Now, I went ahead and I put the graphs down below. We're going to come back to this in a second. The ranges, a lot of times it's easier to, oh, you know what? I just realized I put sorry about that. I put this in the wrong spot. The domain of the original one is equal to the range of the inverse. Sorry about that. That's going to go down here. Okay. The domain of f of x is this. That equals the range of the inverse. So sorry about that. I put that in the wrong spot. Now, if I want to find the range of f of x, the range of f of x is going to equal the domain of the inverse. Now, let's go ahead and take a look. I put both of these functions down here. This one, this red line right here, this is the f of x function. And the green line is the inverse function. So notice that the domain of the f of x, the domain right here of that goes from -7 to infinity. Oh yeah, it is -7 because there's a +7 here. So it should be a minus here. Apologize for making these mistakes today. I'm not sure why I'm making mistakes today. This is going to be from -7 to infinity from the graph. Okay. Now from that, the range, let's look at the range of the original one. The range of the original one, notice that the range there, if I have this red line, the only part that I see, the only y values the graph is using is actually positive y values. I don't see anything below. So for the red line, the range of f of x is going to be from 0 to infinity. So I'm just going to read that off the graph. So the range of that is equal to, here we said 0 to infinity. The range of the original one is equal to the domain of the inverse. So that means now I know that the domain of the inverse is equal to also to 0 to infinity. So I think it helps actually to find the domain and range of the original one first, and then you'll know what to do for the inverse, because automatically you can use these definitions right here in order to write that. So again, domain of the original is equal to the range of the inverse. The range of the original is equal to the domain of the inverse. So I found the domain and range of the original one. Automatically, I was able to get domain and range of the inverse. Now, what you might be wondering is, okay, if I have x squared minus 7, isn't that a full parabola? So why don't I have a full parabola here in this case? Well, the answer to that is because the way these definitions work, the domain of the inverse has to be the same answer as the range of the original one. So since the range of the original one was 0 to infinity, that means the domain is only from 0 to infinity here. Remember that in order for equations to be inverses, they have to be one-to-one function. If I have this full parabola here, all the way across, and it's a full U shape, that's not going to pass the vertical line test, because if I draw a horizontal line and I have a parabola, that means that's going to hit I'll have two different x values for a single y value, and then it's not going to be one-to-one. So actually, in fact, I have to have a restriction on my inverse. My inverse is only restricted from 0 to infinity. So you might want to say that the inverse here is only for values that are greater than or equal to 0 in this case, because then I will actually, in fact, have a one-to-one function. So putting that domain restriction on it allows this function to now actually be one-to-one. Otherwise, if I had the full thing all the way across, it would not be considered one-to-one. So that's why domain and range is actually very important when you're talking about these inverses, and that's why there's a lot of homework questions that will ask you for domain and range. As you go through and you do these, there'll be some questions where it's going to ask you for that. Now, next thing I'm going to take a look at, the next couple of questions in this section have to do with finding the inverse of a fraction on that. Okay, so we're going to do some fraction problems. with this for finding the inverse. Okay, so we have 2x minus 3 over x plus 4. We're going to find the inverse. So we're still going to do the 3-step process for finding that. So here is, first of all, I want to get rid of the f of x, replace it with a y. So we have that. And then step number 2 says that we have to switch the x and the y. Now there's only one y, it gets replaced with an x. Because there's two x's here, both of them get replaced with a y. So that's what makes this problem different from the ones before. We have more than one y value we end up with when we're done here. So we switch the x and the y, we got that. Step number 3 would be to solve for the y. Now, in order to do that, we have to get it out of this fraction form. So what I'm going to do is I'm going to take both sides of the equation, and I'm going to multiply both sides of the equation. So this is like x over 1 here. I'm going to multiply both sides of the equation by y plus 4. You could also cross multiply, but I'll do it this way. By multiplying both sides by y plus 4, this is a 4 down below here. Okay, by doing that, you're going to eliminate the y plus 4s on this side, then you don't have a fraction anymore. If I multiply this, I get xy plus 4x, and that's equal to 2y minus 3. Okay, so those cancel out, and I get this. I need to get all the y's on one side of the equation in order to be able to solve for it. So I'm going to move this 2x term over to the other side, and I'll do that up here. I have xy minus 2y. I still have the 4x over there. Okay, and so again, what I did was I just subtracted the 2y over the other side. Now what I'll do is I'll move the 4x over the other side. That's going to become negative. So I have xy minus 2y equals negative 4x minus 3. I'm going to factor out a y because I noticed I have a common factor. This is actually the reason why you want to get both the y's together, because once you have them both together, we know that we have a common factor for those. So I'm going to pull out a y. We get x minus 2, just like that. Now that I've pulled out the y, this is the whole purpose for doing that. If you factor out the y, then you can divide both sides by x minus 2, and you end up with one y left over. So if you divide both sides, you get negative 4x minus 3 over x minus 2. And that right there is going to be your answer. Of course, step number 4, we do have to put the inverse in there, inverse notation for that, negative 4x minus 3 over x minus 2. And that would be it. Now, even though it doesn't ask for it here, I'm also going to find the domain of this one. So domain of the original one, just to get some practice on domain if we have a fraction. It's basically any number except the one that causes the bottom to be a 0. So if I put negative 4 into the original one, that's going to cause division by 0. So my domain is going to be every number except for 4. So I'm going to have negative infinity to 4, and then from 4 to infinity for that. Now, for a question like this, for 2x minus 3 over x plus 4, to get the range for something like this, you probably want to take a look at the graphs. There is one question in the homework that has some kind of has a fraction. It's not as complicated as this one. I think the one in the homework has just a number on top instead of something like this. But just to let you know, if you wanted to go ahead and find the range, I would highly recommend that you just go ahead and graph it first and see on there. And so I would go ahead and graph it and then see from there what it looks like. Again, that would help you to find the range on something like this. But yeah, so I recommend go ahead and graph it, and then when you graph it, that's going to tell you the range on that. Now, one thing to point out on this, when you graph something like this, in fact, let me go ahead. I think we got enough time. Just want to make sure we have enough time to cover everything. We'll probably go the full class period today, but I do want to go ahead and show you this in Desmos. Desmos.com is a website you can go to in order to graph something like that. So let me go ahead and I'm just going to pull this up for you here, the Desmos graphing screen. And so when you see this, let's go ahead and put in our function. We have 2x minus 3 and divide by in the bottom x plus 4. And the nice thing about doing something like this is you can zoom out, you can zoom in, you can move this around. And so for something like this, we see that originally we had -4 was not included on our domain. So -4 right here was basically, you see we have a vertical asymptote. Now, something about this that we also see here is we have something that's called a horizontal asymptote. We're going to talk about this more when we get into the rational functions. There's a whole section that we'll do kind of on the next, that's not going to happen to like the second or third test where we talk about that. But just to let you know, these type of graphs that have the characteristics of these is basically you have a vertical. That means that the -4 that we found was not included. It causes division by 0. Whatever number that causes division by 0, the graph does this kind of thing where it goes up and it goes down on that. Also, we see here that we actually have a horizontal asymptote as well. Now, this means that the graph is going to come very, very close to, but never cross the horizontal axis that we have here. So this is saying that the graph is never going to reach 2, the value of 2. Now that's important because that is going to affect your range. So let's go back to the other screen. We see here that the y value is never going to reach 2. So let me go back to the notes because I want to talk about that. And by the way, this should have been a -4, not a +4 for each of these. But the range, and this is still the range of the original one. Okay, so the range for that is going to be -infinity to 2, and then from 2 to infinity. Okay, it's never going to reach the y value of 2, and that's what we found from the graph itself. So now we have our domain and range of the original one. We can automatically find domain and range now of the inverse now that we know what this is. The domain of the original one is going to be the range of the inverse. The range of the original one is going to become the domain of the inverse, and that's how you do that. So if you just find domain and range of the original one, then we don't have to go through all those steps for finding that for the inverse. Okay, so for this one down here, the domain is going to be -infinity to 2 to infinity. And then that's because this is the range of the original one, and the range of the inverse is equal to the domain of the original one. So -infinity to -4, -4 to infinity. Okay, so that's how you find domain and range of each one when you have a fraction like that. Okay. So you might want to use a little technology for that one, especially the one that has a fraction. There is one like that in the homework that you'll have to take a look at. So make sure you know how to do that one. All right, so next one that we'll do is this one. We're not going to do domain and range on this for sake of time. This is the last problem that's in this section, so I just want to make sure we have time to cover 2.6. All right, so this one I'm just going to run through the 4 steps only on that. So step number 1 is to replace the f of x with a y. So I want to do another one of these because there's like 2 fraction problems that are in the homework. So I just want to make sure we understand how to do a problem that's like this. Okay, so we have y equals 3x minus 5 over 2x minus 3. Step number 2 is to switch the x and the y. So 3y minus 5 over 2y minus 3. Step 3 is to solve for the y. So as before, I'm just going to multiply both sides by the common denominator, that's the denominator here, 2y minus 3. And so I'm just going to multiply both sides by that. If we do that, the 2y minus 3 is going to cancel out. And so then let's keep on going with this. We multiply by the x, we get 2xy minus 3x, and that's going to equal 3y minus 5 right there. And then we want to get all the y's on one side of the equation. So I have 2xy right here. So basically what's going to happen is this 3y, if we move it across the equal sign, that's going to become negative. But if we take the 3x that's here and move it over the other side, it's going to become positive. So we basically just swap places with the 3x and the 3y. We just swap places with those, and we end up getting this right here. Now that we have this, we have all the y's on one side of the equation. We want to factor out the common factor, which is a y. And when you do that, you get 2x minus 3. Pen is glitching out here. 3x minus 5. Okay, so if we factor out the y there, we get this. And if you divide both sides, we get something interesting that happens as a result. Is we actually get the same thing that we started with. We get the original function, which means that the original function is actually its own inverse. This would be step number 4, is to put the inverse notation back in again. So notice we get exactly the same thing as what we started with. Does that mean that we made a mistake? No, actually. It is possible for you to get the original function. Now this only happens, it's pretty rare, but it only happens when the original function, if the original function is already symmetric about the line y equal x, which this is. If you were to take a look at a graph of this, 3x minus 5 over 2x minus 3, you'd find that it's already symmetric about the line y equal x. And so if it's already symmetric about that line y equal x, that means that you're automatically going to get itself for the inverse. That's what's going to happen for this particular problem. Again, it's pretty rare that occurs, but it is possible for that to happen on these type of problems when it occurs. So I'm actually I'll do a quick, we'll go back to Desmos here to show you that one. And I'll put this in there for you so you can see. Okay, so let's go ahead and give you a second to write that, and I'm going to go ahead and flip to the other screen and show you the graph here. All right, so here's Desmos. Okay, now if you look at that, here's the 3x minus 5 over 2x minus 3, and we have the y equal x graph. Notice what happens right here. This is the line y equal x. You notice here, this is already symmetric. If we take this red line and fold it over the blue line, it's going to end up overlapping itself on top of here. So if the original function already has that symmetry, then it makes sense that when you find the inverse, you're just going to get the original function that you started with. So in this case, the original function is its own inverse. It's pretty rare, but that can happen on that. So you may not necessarily be wrong if you do something like that. It may just be that the function that you have might already be symmetric about the line y equal x. I just wanted to show you that visually to show you what's going on with it. So now let's go back to the notes. Okay, so we got going back to the notes that we have here now. And so this is the last problem that we have in this section. Just want to make sure everybody has a chance to look at that. And then we're going to go ahead and jump to the last section of notes that we have for this. And we have a half hour left, and that's plenty of time to cover this section. So we'll be able to fully finish this section today as well. So again, 5.2 and 2.6, both of those will be on your test for this week. So jump to this. Okay, and basically what this is, 2.6 is talking about some kind of word problems. Okay, so 2.6, they'll all be linear problems in this section. And there's one in the test that's similar to this first example that we're doing. So that's why we're going to go ahead and cover this one first, because that's the most important that we have. But of course, your homework does have other questions that go on some different things as well. So first thing we'll do is we'll do this first problem. Now, if we read that, again, it's got the word linear in here. Now it's asking to find a linear function on it. So a linear function, what that means is that you're writing something in the form y equals mx plus b is what we have. By the way, this particular section, when you do the homework, I'm going to go ahead and show you before we do this problem here. I want to show you there's a couple problems that are in the homework that actually have worked out solutions on them. And so I want to take a look at one of these. We're not going to do this problem because we don't have time to cover this completely in class. But I do want to go ahead and pull this up for you. Okay, so if you look at this screen here, this is one of the types of problems that you'll have to do. And if you take a look at it on it, so these are just all the problems here have to do with word problems there. If you look at underneath the answer blank, you're going to see this thing that says show detailed solution. I have this for 3 of the problems that are in this section because they're not exactly like the ones that we do in the notes. So if you do show detailed solution, there's a similar problem that's in it, and it walks you through exactly how you want to solve that. And actually, the one that you'll get is very, very similar. So you can follow the similar algebra steps that are here. So you can go ahead and read the work solutions. There's no video that goes along with these, but there is a work solution that you can go ahead and see with that. So that is provided on 3 of the questions. There's only 6 questions actually in this whole section to do. So half of them we'll kind of cover in class because we have similar problems that we'll do for lecture. But then the other ones that don't look exactly the same, you can go ahead and look at these work solutions on that. And that's going to allow you to give you some assistance there on those problems. Okay, so we'll go back to now the notes here. So we've got this here, a manufacturer buys a new machine costing $120,000. It has a useful lifetime of 10 years. And then basically it's saying after 10 years, the thing is only worth $4,000 at the time. That's what we're salvaging it for. That's the value it's worth at that time. So it says find a linear function for the value v of the machine after 2 years. Now it's very important that you make sure you use, when you set the problems up, when you write your answer in MyOpenMath, make sure you use the same variables it's asking you to use. You don't want to accidentally put a y or x in there. We're going to use y's and x's to actually get our answer, but when we type our answer in, we want to make sure we're using what exactly is actually shown here as far as the variables that's using. What I'm going to do here is I'm going to write this as 2 points. Okay, so yeah, these 4 zeros there. Okay, I'm going to write an x and a y coordinate for that. The x is going to represent our years, and the y is going to represent the value. If it's brand new, that means at 0 years, it's worth $120,000. It also tells us that after 10 years, the machine is only worth $4,000. So this is like X1 and Y1, and this is going to be X2, Y2. So I'm coming up with a set of 2 different points in this kind of problem. So anytime you have some kind of depreciation where a machine's worth this much, then it's worth this much later, you're going to want to go ahead and do the same setup on this kind of problem. There's one like that in the homework. What we're going to use here is we're going to go back to and use a formula we talked about before in a previous section. It's the slope formula, change in y over change in x. We're going to go ahead and do that for this. Okay, so we have that one. We're going to put the points in that we've already labeled already. So y2 minus y1, we have 4,000 minus 120,000 there. On the bottom, we have x2 minus x1, 10 minus 0. Notice that we are going to get a negative number on top. Now that makes sense because you're talking about a problem where you have a machine that's depreciating. If you have a machine that is depreciating, that means it's going down in value over time. So we should expect our answer our answer for slope to be negative. We get out negative 116,000 we get here divided by 10. So that's just going to get rid of one of your zeros. And so we get negative 11,600. Now what this means is that every year the machine is losing $11,600. That's what that means. Okay. Kelly's Blue Book kind of works in a similar fashion with cars. Some cars are more linear when it comes to that. So when you buy a new car, might be worth 120,000, and then it's not going to go down in value that much. But some could actually go down that much. After 10 years, it could only be worth $4,000. So Kelly's Blue Book, it works in a similar fashion depending on what model that you have. Some more closely resemble linear than other ones do. Okay, so now that we have this, okay, this point right here, this is actually the y-intercept. Now, the reason why I know that is because the x value is 0. So whenever the x value is 0, automatically that gives you the y-intercept. So now we have a slope and we have a y-intercept. So if we want to do y equals mx plus b, we could do y equals negative 11,600x and then plus 120,000. And that right there would be a linear function. Now, it's not the answer here, but with y's and x's, that would be the case with this. Now, the reason why this is not our answer is because it's not using the variables that it's asking us to use. Okay, so instead of the x here, I want to use, that's the number of years. So I need to put a t in there instead. Okay, so that's a t, first of all. Okay, so we have that. Okay, next. The value of the machine is v. Now, the function of the machine after t years, that actually is, we want to put v of t. You don't want to put v. You just put v. That's not function notation. Remember, it says function here. So function means we have to write it as a function. So we have a v and we put in parentheses a t afterwards. Okay, so right here, erase a little bit of this y here and put in the, so again, a function there means that we want to put v of t right here. Okay, so this is the correct answer that you would put v of t equals negative 11,600 t plus 1,200. Now this is 12,000. This is what you type in, and that would be the correct answer. Okay, so you have to make sure you use the variables that are given in the problem itself. It depends. Each problem has different variables, so just make sure you use the correct one there. Okay, so next, we have a company is planning to manufacture a certain product. The fixed costs, we have variable costs here, and we have how much is sold. This one, we want to make sure we know a couple definitions in order to do that. We have the word profit that's here. So first of all, we have the profit is equal to the revenue minus the cost. Okay, so profit is revenue minus cost. That's the definition that you have to know on this problem. Another one that you want to know is the formula for revenue. Revenue equals price times quantity. Okay, so we have to know those two definitions in order to do this particular problem here. Okay. Now we have to come up with a cost equation, and we have to come up with a revenue equation, and then we're going to subtract those to get the profit. Let's first come up with the cost function. Let's come up with that first. Now the cost, and that's in the first sentence, it's second sentence. The fixed costs are 500,000 and it costs $400 to produce each product. So I want to come up with a C of X equation. Now I have 500,000. I have to pay that no matter what. That's for probably the factory and initial cost of equipment, things like that. And then I have the variable cost, which is labor or wear and tear, maintenance, those kind of things. That's just going to be 400x. Your total costs are going to be the fixed cost plus this variable cost. And we're using x to represent each unit that we have. Okay, so x, it didn't give us any particular variables to use here, but we'll go ahead and use a p for profit and an x for the number of units that we have. Now, next thing we have to find is the revenue function. Okay, so the revenue function, okay, revenue is equal to price times quantity. Now the price is how much it's sold for. That's going to be $600. And then we're using X for the quantity. That's the number of units that we're selling. So now I have my cost equation. I have a revenue equation. I'm now ready to do the profit is equal to the revenue minus the cost. Okay, so if I can write here. Okay, revenue minus cost. Your profit then is going to be equal to the revenue function, 600x, minus this is the cost right here. So now we just have to subtract this. Now notice I'm putting all this in parentheses because you're subtracting the entire thing. Okay, so I have to subtract all that from them. So you get, if I distribute the minus sign, I get minus 500,000, and I get minus 400 as well. So negative has to apply to both of those, and I just have to simplify this, and I get 200x minus 500,000, and that right there is the profit equation. That would be the profit in terms of units sold X, that's a quantity. Okay, so that's the profit. Now, the other thing it asks for here, it says how many units must be sold in order to break even. Now, break even means that your revenue, there's two different ways that you can tell if you have a break even. So if I have break even, it means that the revenue equals the cost. So R of X equals C of X is one way to do it. Or if the profit equals 0, that's another way to tell the break even. Okay, so right there, if the profit equals 0, that means you didn't get a gain, you didn't get a loss. That means you exactly broke even. All right, so if I want to find out the break even point, probably since I already have the profit function there, I'll just go ahead and set that equal to 0. Just like that. So I'll move this over and then divide. If I divide both sides by negative 200, I will get a positive result as to be expected there. So dividing it by 200, we're going to get 2,500. And this will be in terms of units. Okay, so that's units there. That's the number of units that I have to sell to break even. If I sell less than that, that means I'm at a loss. If I sell more units than 2,500 with this model, it's telling me that then I'll be making a profit at this point. So I got to sell more, whatever it is I'm selling. I got to sell more than 2,500 in order for it to be profitable based on that. Okay, so that one. So next one we'll do. Okay. All right, so we got an open box. Is to be made from a square piece of material that we have listed there. And there's a question like this that's in the homework that's similar to this. Okay, so for this here, open box is made from a square piece of material, 24 inches on a side. By cutting equal squares. So these little squares here that you see, they're actually going to be, so these little things here, I'm gonna shade them. I shade that, this one here and this one here. Those right there, those are going to be cut out, and then it gets folded up to make this box that you see right here. We want to write an equation for the volume of the box as a function of x. Now, I kind of did a lot of this for you, but you'll have to do this in the homework question itself. So basically, if I have, it's telling me that all the sides are 14. Well, if I have 14 all the way across and I have this x and I have this x here, I'm sorry, 24, not 14, 24 inches on a side. I have 24 inches on a side, and I have this x and this x that I'm removing and cutting and taking away. Well, that means that the whole entire side is just going to be this part in the middle here is going to be 24, the whole thing, 24 minus this x and minus that x. That's where you get 24 minus 2x from. There's a square. The same thing's going to happen up and down here. This dotted line part is also 24 minus 2x. The whole distance is 24 all the way up and down like that. 24 minus this means this middle part here is 24 minus 2x as well. Okay, so we have a 24 minus 2x on that dotted line, and we have 24 minus 2x on this dotted line right here. Well, when you fold the box up and put it there, you get this side and this side. That's the base of the box. And then the height, if you're folding this, it kind of comes out of the screen, if you can think of that. You're kind of folding it towards yourself. If you fold it towards yourself, that means that that's the height of the box is going to be an x right there. Now, the volume is equal to length with height. Okay, so anytime you have a box or a rectangle, doesn't matter. It's length times width times height. Now, in this case, we have volume here. Length and width are both the same, 24 minus 2x, 24 minus 2x. And then we have an x, which is the height. So length, width, height that we have. Now this, we can rearrange this. We can put the x out front first. Because there's two of these things, you can also write it as 24 minus 2x quantity squared. Now you don't have to multiply all this out. It's not necessary to do that. The one it's in my open math it will show the answer all multiplied out, but you don't have to do that. You can actually leave it in the factored form like this. Now, one thing you do want to be careful of here is it does say a function. Then you do want to go ahead and put an x there next to it. Now, I believe that's in the homework. Let me just look to make sure here. Make sure it's actually asking you to, yeah. So then this one, in this case, you don't have to actually type that out. It has a v of x equals on there already. So yeah, so that you don't have to worry about. You just have to type the function in on that one. That's all you have to do there. It says then find the volume when a 3-inch square is cut out. Okay, so now we have the formula. What this means is all you have to do is put a 3 in there for x. X represents how high the box actually is with part you're cutting out. So all you have to do is put a 3 in here to find that one. So 2 times 3, and then this is squared. So v of 3 is equal to 3 to 24 minus 6 here would be 18, like that. So we put an 18 in there. And then we just have to compute that, and that's going to give us the answer here. And so if we put that in there in our calculator, we're going to get 972. Okay, so 972 we get. Now the inch, this will be square inches that cubic inches. Okay, so cubic inches you have, that's the unit on it. Let me actually write that out. Cubic inches will be the unit that you have on it. And so that it actually does ask you to write the units on here. Now, the reason why it's a cubic is because this right here is in terms of inches, and you're multiplying it by an inches squared. So then you get inches cubed, which is the same thing as cubic inches. So whenever you have a volume, it's cubic inches. If it's square inches, that would be if you have an area. Okay, so square inches would be an area, but in this case, we have a volume. So volume will always be the cubic inches that you would have. So you would select that. There's a pull down menu on this problem that you'll do in the homework, and you can just select which unit that you actually have there. Okay, so now let's do this next one. Okay, so this is the last. We have actually two more to do. We're done. So again, we're probably going to take this all the way to 11:20 today, but we will have time to cover all these questions. Okay, so we got the square length of 10x is bent into a shape of a circle. Okay, so basically we have a wire that's like this that is 10x long. Okay, and so we have this, and it is turned into a circle. Okay, so if we take 10x and turn it into a circle like this, okay, what that represents here, if this is 10x all the way around the circle, what that is in fact is that's called the circumference. So for part A here, it says express the circumference of the circle as a function of x. Well, that's just going to be the circumference in terms of x is going to be 10x. Okay, and that's actually all it's going to be. That's simply what it is. Okay, so we have that, and that's all it's going to be. Okay, circumference is simply how far it is all the way around the circle. That's all you have to do there in that case. Next, it says express the area of the circle as a function of x. Okay, so one thing about that is your area is equal to pi r squared, where r is the radius, pi r squared. Okay, and then your circumference is equal to 2 pi r. Okay, so that's the two formulas that you'll need as far as the when you're talking about area formulas. So I want to put those down for you, so that way you have those, because you will have to do that. By the way, you don't have to know any area or volume formulas for the test. If there are any of those that are on there, it's going to be provided for you. So I don't expect you guys to know how to memorize those area and volume formulas, so you don't have to worry about that. Okay, but so we do have those available for you. Okay, next thing we're going to do is we know that that right here, the circumference, we know that to be 10x. We already determined that already. So we could say that 10x is equal to 2 pi r, just like that. We can solve for r and then put it into the other formula, because we have to find something, the area of a circle as a function of x. It has to have x only, not r's. So if I just divide both sides here by 2 pi, then I get 10x over 2 pi is equal to r. And so I can also reduce that and get 5x over pi, because I can reduce the 10 over 2 is this 5 there. So I get 5x, make that look more clear here, x, not a y. Okay, so I have r is equal to 5x over pi. Well, now I'm going to take this and stick it into here, into the area formula. So area, and I'm going to make it a function, area as a function of x is equal to pi times, and I have 5x over pi. All that is going to be squared. So I'm basically just replacing the r with all this here. If I square the top and the bottom on that, I get pi times 25x squared over pi squared. One of the pi's is going to disappear there. And so then I just get 25x squared over pi. and that is going to be my answer for part B. So that one was a little bit harder because we had to do a substitution on that. But that would be your answer on that. So you just did a substitution. Since we know what the circumference is equal to, we set it equal to the circumference formula. We solve for r, and then we stuck it into the area formula because it has to be a function of x, not as a function of r. So that's why we had to get rid of the r and replace it with something that had an x in it. Okay, so this is the last problem that we're going to be doing for today. That's in this section. Okay, so it says a rectangle is bounded by the x-axis and a semicircle, as we see here. Express the area A of a rectangle as a function of x. Now, one thing that I've labeled here for you that you have to pay close attention to is that this part right here is x just from 0 to there. But from here to here, this part is also equal to x as well. So we have x from 0 to there and 0 to there. So the whole entire length all the way across this box is actually going to be 2x all the way across. Now the height of this is going to be a y right here. So I have 2x that goes across the bottom there, 1x for there and 1x for there. X's are always measured from the y-axis, how far you are away. That's why we have 2 x's here, not just one. And the height is y. If I want to find the area of just the rectangle part, that's just equal to length times width. So 2x times y. So let me put that up here. Length times width. That's the area of just a regular rectangle or a box, length times width. I have all that, 2x times the y. So 2xy is the main formula, the main thing I want to use. Now it does say you want to express the area as a function of x. So I need to get rid of this y that's here. The way we do that is notice that it actually gave us the y. Y is equal to the square root of 9 minus x squared. So what I can do here is I can just put in, this is now going to be area as a function of x, since x is the only variable we're going to have in here now. You're going to remove the y, replace it with 9 minus x squared. Okay, so the y goes away. We put it in with the function. So now we have an equation that is all in terms of x. That was all that this question asked us to do here. And then that would be your final answer on that. Okay, and so that would be, that's basically all the notes done from 2.6. So again, there's only 6 questions in the homework. 3 of those are similar to ones that we just did in class today. And the other 3 of them, they have these worked solutions. So you want to go ahead and click on the worked solution. It'll give you a similar problem with different numbers. But it'll kind of walk you through, and that way you'll know kind of how to set that up based on that. In fact, one of the questions also is going to be the one we just did here with the wire. That is one of them that you actually have 2 things. You actually have my explanation here, and you can also read through there's a show detailed solution that's also in here. So if you get the problem wrong, you can, underneath the problem, you can select show detailed solution. That's going to tell you how to do that particular problem. All right, so tomorrow there's just going to be a review. So we're not going to do any new material tomorrow. We're just going to review by going over the sample test. That's going to be what we're doing. Always what we do for review in this class is we'll go through the sample test. So right now, does anybody have any questions before we end today? All right, sounds like nobody has any questions. So I'll go ahead and I will end this meeting. If you think of something, just please send me an email, let me know. Enjoy the rest of your day. See you guys tomorrow.